Hi, thanks so much for tuning in. My name is John Krasniak. I'm a recent master's graduate from the University of Virginia Department of Computer Science, and on behalf of my co-authors Jingyan Ning and Dr. Manor Bell, I'm excited to present our paper, Deep Dynamics, Vehicle Dynamics Modeling with a Physics-Constrained Neural Network for Autonomous Racing. So to start off, let's talk about what exactly is autonomous racing. Other than an exciting motorsport for us robotics fans, autonomous racing is a platform for stress testing the capabilities of autonomous vehicles. Here we have racing competitions where vehicles compete to record the fastest lap or overtake one another at high speeds. And these competitions occur at various scales. For example, F1 10th offers a small scale racing platform, Formula Driverless offers an intermediate scale, and more recently, competitions like the Indy Autonomous Challenge have provided a full-scale platform for autonomous racing. Now, in this research area, us researchers are responsible for writing the control algorithms to dictate how the vehicle changes its steering, throttle, and brakes so we can push the vehicle as closely to its limit as possible to make it a very competitive race car. We don't want to push too far. Because in racing, when we push beyond the vehicle's limits, we can have incidents like spins or collisions. Now, not only does this knock you out of the race, but as my advisor can attest to, crashes are quite expensive. So we'd like to avoid these at all costs. So again, in order to have a competitive race car, we need to have a control algorithm that can push it as hard as it possibly can, but do it very precisely and very carefully. Now, a common technique that researchers use to achieve this level of precise control is basing their control algorithm around a vehicle dynamics model. Let's take a look at a couple of different models that we could use and where they lie on this axis of accuracy versus ease of identification. One model that is commonly used is the dynamic single track model. Here we're going to assume that the vehicle has two wheels, one front and one rear, which is why it's commonly called a bicycle model. And we're going to use sets of coefficients that we've derived that describe dynamic properties of the vehicle's tires or drivetrain to estimate the forces that are inflicted on the vehicle's wheels. And with those forces, we can then estimate the predicted future state of the vehicle. Now, this model can be very accurate, but it really depends upon precisely identifying values for those coefficients that I just mentioned, which are very difficult to identify. Now, on the other hand, we could say, who needs physics? We can tell Isaac Newton to take a hike and say, instead, we're just going to use a purely data-driven approach. So for example, we could use a neural network that's going to be given a historical horizon of vehicle state and control inputs, and then just use that to directly predict the vehicle's future state. Now, this is a very easy approach to identify. It just requires a data set of the vehicle driving, but it's not guaranteed to have high performance. Since this is a supervised learning approach, if the neural network encounters data that it hasn't seen before, it could poorly generalize as out of distribution data. So a technique that's become popular within recent years is merging the benefits of data-driven approaches with the accuracy and robustness of a physics-based model to create this hybrid model. Let's talk about how that works. So here we're going to give a neural network a historical horizon of vehicle state and control inputs. And we're going to use that to predict coefficients for our physics-based model. So for example, coefficients for our dynamic single track model. Now, we don't know the values of these coefficients, so we can't train our neural network to predict these directly. So instead, what we're going to do is take those estimated coefficients, and along with the vehicle's current state and control input, we're going to feed that into the state equations for our physics-based model, which we can then use to predict the vehicle's future state from time t to time t plus 1. Now, since we can observe the state of the vehicle at time t plus 1 in our data set, we can directly compute the loss here using the difference between the predicted and observed future state. And as we backpropagate through the neural network, we're going to indirectly teach it to accurately estimate coefficients that are going to predict the vehicle's motion. In their paper that they introduced at IROS in 2022, authors Kim et al. Proposed the deep projector model, which is a hybrid model that is used to predict coefficients for the dynamic single track model. Here they're going to estimate coefficients for the projecta magic formula tire model, which is going to be in red the coefficients B, C, D, and E with the subscripts F and R denoting coefficients for the front and rear wheels. And they're also going to use the neural network to estimate the longitudinal force Fx that is applied to the vehicle's rear wheel. And then once we have those estimated coefficients and that estimated force, we can then use the Projecta magic formula tire model to estimate the lateral forces that are inflicted on the wheels. And combine that, we can then predict the vehicle's acceleration and then future state. Now, while this is a great approach, it does suffer from 3 key limitations that limit its feasibility for use in a racing environment. First, there are no constraints here on the estimated Projecta coefficients. And that's important because these coefficients have physical meaning. And if we have coefficients that stray beyond their physically meaningful range, the model is no longer going to make physical sense. Let me show you what I mean by that. So here we have 4 different plots that show the estimated lateral force generated by the Projecta model as a function of the vehicle's side slip angle. And each plot has different Projecta coefficients used to generate it. On the left, we have plots for 2 valid models, and we see relatively expected behavior. We have the lateral force increase as the vehicle's side slip angle increases until it eventually reaches some horizontal asymptote. Now, on the right, we have scenarios where just one Projecta coefficient is outside of this physically meaningful range, just one. And that can result in behaviors like the direction of the force changing as the side slip angle increases or oscillations in forces. And again, we're not going to see this on a real vehicle. The second limitation of the Projecta model is that it has no physics-based drivetrain model. So here they use the desired velocity as a control input and then use the neural network to predict what force the engine is going to generate as a result of that desired velocity. So the issue here is that we don't have an understanding of how the vehicle's throttle or brakes impact the forces that the vehicle experiences. So if we wanted to have a longitudinal controller use this model, all we can do is use the desired velocity and feed that into a PID controller, which isn't going to be as precise as a model-based controller. And now lastly, the Projecta model assumes that the vehicle's moment of inertia is known. Now, it is possible to get rough estimates, but in racing, again, we need very precise estimates of these coefficients to have a very precise model, because when your vehicle is traveling over 100 miles per hour, we don't want to have any room for error. And attaining this precise moment of inertia is very difficult unless you have, for example, a CAD model of the vehicle. So in our work, we introduced deep dynamics to address these limitations. Similarly, we're going to start off with a historical horizon of vehicle state and control inputs. And then we're going to feed that into a neural network to predict 3 different sets of coefficients. First, we're going to have coefficients for our Projecta magic formula tire model. Second, we're going to have the vehicle's moment of inertia. And third, we're going to have coefficients that describe a linear drivetrain model. Now, importantly, we're also going to constrain the value of each coefficient using what we call our physics guard layer. Here we're going to use the known bounds for each coefficient and scale the coefficients estimated by the neural network using the sigmoid activation function with these upper and lower bounds. So again, we're ensuring that our neural network is always going to predict meaningful coefficients. Now, once we have those coefficient estimates, we can use the current state and control input of the vehicle and feed that into our Projecta magic formula tire model to predict the lateral forces that are going to be inflicted on the wheels, as well as our drivetrain model to predict the longitudinal force applied to the rear wheel. We can then use those forces and the estimated vehicle moment of inertia to predict the vehicle state at time t+1. Okay, now that we've established the structure of the model, let's talk about how we can train it. In our work, we collected data from 2 different sources. The first source we collected data from is a 1/43 scale RC race car simulation environment called Bayes Race. Here we used one track to collect the training data set and one track to collect the testing data set. We also did a similar approach for our full-scale Indy race car that our university uses as part of the Indy Autonomous Challenge. We have a run at the Putnam Park Road Course consisting of our training data set and a run at the Las Vegas Motor Speedway to consist of our testing data set. Now, we wanted to benchmark our approach against the Projecta model, but as I mentioned, the Projecta model assumes that the vehicle's moment of inertia is known. So we wanted to test 2 different cases here. The first case is going to be when we give the Projecta model the ground truth moment of inertia. So this is known in the simulation environment. It's a parameter that we can configure. And then on the real vehicle, we have an estimate that the vehicle manufacturer gave us. So we can give that to the deep projectile model here as well. Now, this is more of an ideal scenario because, again, these aren't typically available. So we also wanted to test a scenario where the vehicle had a error in its estimated moment of inertia. So here, we're going to give the deep projectile model moment of inertia estimates that have an intentional error added to them. So one where we reduce the ground truth value by 20%, and one where we inflate it by 20%. We then benchmarked all models we trained in terms of open loop predictions over a prediction horizon. So here we have the real vehicle traveling around the Las Vegas Motor Speedway with the ground truth trajectory of the vehicle shown in blue. And we use the coefficients for each model that we trained to predict the vehicle's trajectory throughout this turn. Now in the bottom right, we have the average displacement error and final displacement error, each trajectory predicted by the deep dynamics model and the deep projectile model, given the ground truth moment of inertia. And we can see that deep dynamics is more accurate throughout this turn. Additionally, we also conducted closed loop testing in our 1/43rd scale simulation environment. Here we use the coefficients estimated by each model, and we feed that into a nonlinear model predictive control algorithm to have the vehicle drive around the track. Here we can see that deep dynamics not only exhibited a faster lap time and a higher average speed, but it also was able to navigate through the circuit without violating the track boundaries once, whereas the deep projectile model had multiple violations in each scenario. To summarize, in this work we introduced deep dynamics, a physics-constrained neural network that is appropriate for vehicle dynamics modeling in an autonomous racing environment. We also introduced the physics guard layer, which gives our neural network the name physics-constrained by constraining the estimates of the neural network to always be within a physically meaningful range. And lastly, we conducted both open and closed loop testing using a simulation environment and data collected from a real-world autonomous race car. I'd like to share that we've released the code and data associated with this paper open source, so feel free to access that, the QR code on the left or using the link. And if you're more interested in checking out the Indy race car data, you can also visit the link I have on the right for a data set consisting of multiple runs through the multiple teams have compiled. Thanks so much for your time.